Okay, so we're going to do problem 8.22. We're going to look at this water bucket problem. This water bucket problem is one of the tricky problems in physics. And the idea is that we're swinging this bucket as slow as we can so that the water does not fall out of the bucket. And that is the tricky part, because the question is, what do we draw a force diagram on? Are we drawing it on the bucket, on the water? How do we deal with that? So this is one of those tricky problems that you want to think of the water as the object. Okay, so we're going to be drawing our force diagram on the water, not the bucket. And let's take a look at let's look at that at the top. Okay, so we're trying to figure out what is this minimum angular velocity. We'll talk about, we'll get to that shortly, but we want to know what's the slowest velocity we can spin this at so that the water does not come out. Okay, let's draw a force diagram for the water when it's at the top. Okay, so I'm just gonna make this like a blob. There's the water. And we've got the weight acting downward as always. And we also have the normal force from the bucket. So we have to ask ourselves, well, what direction is that normal force going to be acting? Okay, well, remember, whenever we have any kind of rotational motion or circular motion, the idea is we have to have, what is it that we need to have in order to maintain that curve? Well, we need a centripetal acceleration or a net centripetal force. Okay, so in this case, what direction is the normal force going to be acting? Well, if we didn't have the normal force coming from the bottom of the bucket, then the water would just fly out of the bottom of the bucket when we got to the top of the curve. So that helps us to see that the normal force has to be acting downward when the bucket is at the top. Okay, so now we have this normal force also acting downward. Both of these forces are acting toward the center of the curve. Both of them are positive as far as our sign conventions go for the centripetal axis. Okay, so the faster we swing this, ask yourself what's going to happen if we swung this faster and faster. What would change in our force diagram? Would the weight change? No, the weight's not going to change because the weight just has to do with mass and the acceleration due to gravity. That's not going to change. What about the normal force? If we swing this faster and faster and faster, then the requirement from the bottom of the bucket is going to get stronger and stronger. So that force from the bottom of the bucket, that normal force, is going to have to get greater and greater and greater to maintain that curve if we're going very fast, and we need a stronger centripetal force to maintain that curve. Okay, so let's now think about if we went slower and slower and slower. Okay, so if we go really, really slow, what if we just held the bucket upside down? We didn't swing it, we just held it in place upside down. Of course, the water's all going to fall out. Well, in this case, there wouldn't be any need for a normal force. There would be no normal force really acting against the water. The water would just be, well, free falling, just be falling because of its weight. Well, the key here is we want to figure out how fast to swing this so that the normal force is going to equal 0. All right, so we have the slowest rotation is going to be when the normal force is equal to 0. That will still allow us to maintain, the water will still stay in the bucket. And you might say, well, how is the water going to stay in the bucket if there's no normal force? Well, think about what's required for the water in order to maintain a curved path. You need to have a centripetal acceleration. You need to have a center-seeking sum of your forces. So it's not necessary that we have a normal force acting. What's necessary is that we have a net force acting toward the center of the circle. Well, at the very top of the arc, downward, that weight acting downward, that is the center of, is acting toward the center of the circle, but only at the top. At any other point in the curve motion, the weight would not be acting toward the center of the circle. But at the very top of the motion, the weight is acting toward the center of the circle, so it's a centripetal force, but just for that brief moment. Okay, well, so now really we get down to just saying that the normal force is equal to 0, and we just have the weight acting downward. Okay, so now let's apply Newton's second law to that. Now that we know that we really just have one force that's acting. Okay, and remember we're using the centripetal direction. Okay, so the centripetal force is going to be equal to mv squared over r. And just like always, we're going to fill in the left side with the player roster. Who are all the players? What teams are they on? So in general, we had the normal force plus the weight acting toward the centripetal, toward the center of the curve. I know we said that the normal force is 0 here, but just so we have it for clarity. Okay, then on the other side, we have our mv squared over r. Okay. So now we can also pull in the relationship between the linear velocity and the angular velocity that we learned, I think, back in chapter 2, I believe. And that is that v is equal to r times omega, where omega is the angular velocity in radians per second. Okay, so if we make that substitution, let's pop that in for v over here. Okay, so we have the weight equals m, okay, and then we're going to have our the r omega, that gets squared, okay, all over r. Okay, I'm going to substitute mg for this. This is the mass of the water, by the way. Okay. And then over here we get this, and we get one of the r's to cancel. We get the m's to cancel. Okay, and if we solve this for omega, which is what we're trying to find, that's going to give us, it's going to be g over r square root. Yeah, okay. So look how nice that expression came out. We really, notice that the only thing that we really need to know here is just what is the radius of the curve of the circle. We don't even need to know what the mass of the water is. It's irrelevant. Yay. Okay, so let's figure out what this is. Let's pop in some numbers. Squared, okay, and our radius, let's go back up here to our radius. The full entire radius is going to be the 65 centimeters plus the 35 centimeters, or essentially 1 meter. Okay, so those two are going to add together. I'm just going to put this here. The radius is going to be 65 centimeters plus 35 centimeters. Okay, and that's going to equal 100 centimeters or 1 meter. Okay, so 1 meter. Let's put that down there. Okay, let's see what we get. Okay, so let's see. Square root of 9.8. Okay, that gives us something like 3.13. I'll just keep a few extra sig figs on there. And this is going to be in radians per second. Okay. Now, the question asks us for what is the minimum angular velocity in RPM. All right. So let's go to the RPM. Let's convert our radians per second to RPMs, or revolutions per minute. Okay, so we're going to start with what we know. Okay, we have radians per second. We don't want radians, so we're going to put radians on the bottom in the next spot. Okay, and from radians we can go to revolutions. Okay, We know that 1 revolution is the same as 2 pi radians. That gets rid of our radians, and now we are at revolutions per second. So let's get rid of the seconds. Let's switch them for minutes, and 60 seconds, 1 minute. Okay, so let's see what that gives us. All right, so that comes out to 2 sig figs. That rounds to 30. And that's going to be revolutions per minute, or RPM. And that's our answer.